Section 3.2, Logarithmic Functions and Their Graphs. We're going to recognize and evaluate logarithmic functions, and we're also going to graph them. Before we talk about a logarithmic function, we have to understand that an exponential function is a one-to-one function, and we know that because the graph of an exponential function passes the horizontal line test. So if it is a one-to-one function, then the exponential function must have an inverse function, and we call that inverse function the logarithmic function. So exponential and logarithmic are inverses of each other. They undo each other. So a logarithmic function, by definition, for every x value greater than 0 and a is greater than 0 and a cannot equal 1, y is equal to log base a of x. And that's how it's read. Log base a of x. If and only if x is equal to a raised to the y power. So this gets right back to the exponential. So this represents the exponential part. This equation is your logarithmic part. And so we have a couple stipulations that we need to make sure that we're aware of, where a is greater than 0 and cannot equal 1, which relates right back to the exponential. Your base right here has to be greater than 0 and cannot equal 1, otherwise it wouldn't be exponential. And then the x value, which is, in this case, it's written as your x, but that's your output of your exponential. And your output, we talked about the range being greater than 0. So now, for a logarithm, that's your input. And that's why this is going to become so important, is that the x value must be greater than 0. So we'll talk more about that as we go through logarithmic functions. But that is going to be definitely very important that we understand that that value must be greater than 0. The equations y equals log base a of x and x equals a raised to the y power are equivalent. A couple things to kind of look at is the bases. That's base a. That's base a. Also, a logarithm, this whole thing, is equal to this, and when you change it to exponential, that y value is the exponent. So something you're going to hear me continue to say is a logarithm is an exponent. So this logarithm, log base a of x, is equal to y. That y is the exponent in exponential form. So a logarithm is an exponent. So for example, 16 equals 2 to the 4th. If we wanted to write that as a logarithm, you have the base of the exponential as 2, so that's the base of the logarithm. You have the exponent as 4, and the exponent of the logarithm, which a logarithm is an exponent, is equal to 4, and then your 16. So 16 equals 2 raised to the 4th power is equivalent to log base 2 of 16 is equal to the is equal to 4. A logarithm is an exponent. So once again, you can see that this whole thing is equal to the exponent of 4. Think of another common inverse function that we know. All right, square root of 36 is 6. How do you rewrite that inverse? And so I want you to just pause and kind of think about this for a second. How do you take the square root of 36 equals 6 and rewrite it using its inverse? All right, hopefully you took a second to do that. Square root of 36, remember the index is 2. So we could rewrite this as 6 squared is equal to 36. And so one is written as a quadratic, 6 squared. The other one's written as the square root of that. So we have other inverse functions that we have dealt with before. This one is just somewhat newer to us in terms of exponential and logarithms, but they work the same way. So the first thing that I want to look at is just being able to take a logarithmic equation and rewrite it exponential. So if we have log base 5 of 125, what does that mean? And how can we write that exponentially? Well, it's log base 5. So if we're going to rewrite this exponentially, we want the base to be the same. So base 5, a logarithm is an exponent. So 5 to the 3rd is equal to 125, which is a true statement. B, log base 4 of 1/16 equals -2. So base is 4, Logarithm is the exponent, so that's negative 2. So 4 to the negative 2 is 1/16. Just being able to do that back and forth is going to be important. All right, let's go the other way. Write an exponential equation in logarithmic form. So now we know that the base is 3, so we will do log base 3 of 81 is equal to the exponent of 4. Once again, on the next one, log base 8 of 2 is equal to the exponent 1/3. Okay, so this is just working on going back and forth between the two inverses. All right, I want you to evaluate a couple of logarithms here, just to kind of get you started. Log base 2 of 32. So 2 raised to what power is going to give you 32? And you can either think about that in your head as to what that represents, or if you struggle with that, 2 raised to what power? Well, 32 can be rewritten as 2 to the 5th, and so therefore x must be equal to 5. So log base 2 of 32 is equal to 5. 2 to the 5th power is 32. So 3 raised to what power gives you 1? Now you can't get a common base here, but what raised to any power is going to give you 1? And that would be 0. So 3 to the 0 power is equal to 1. This one we have 9 raised to what power is going to give you 3. Now this number is 9 to the first would be 9, and 9 to the 0 would be 1. So it's somewhere in between your 0 and 1. Okay? So if you remember, when you raise things to rational exponents, they're your radicals, your square roots, cube roots. So on this one, 9 to the 1/2 would be 3, because that's the square root of 9 is 3. So this is equal to 1/2. That's the exponent. And then the last one, 10 raised to what power is 1 over 100? Well, you can rewrite 1 over 100 as 1 over 10 squared. And then to get that to the numerator, you can do 10 to the negative 2. So therefore, that would be negative 2. So 10 raised to the negative 2 is 1 over 100. So on that, you're just looking at kind of rewriting as exponential and using your exponential properties in terms of thinking about what those values represent to figure out what the logarithm is. All right, on example 4, use a calculator to evaluate the function log base 10 of x. Now log base 10 of x is your common logarithm. So this is the one that's on your calculator. So when you press log on your calculator, when it's log of x, that's base 10. So on your calculator, you just have to press log, and if x is equal to 9, the question is, what is log base 10 of 9? And you can see on the calculator screen there, 0.95424. And so log base 10 of 9 is approximately 0.954 rounded to the nearest thousandth. The second part of this, what I did was to kind of work backwards is, if that's 0.95424, then that's saying that 10 raised to that number should give you 9. So it's just kind of showing that check that it is correct here. B, we have log base 10 of 1.8. Plug that into the calculator and we approximately get 0.25527, so that'd be approximately 0.255. Once again, showing that if I take 10 raised to that power, I should get the 1.8 back. Now on the last one, you can see that there's something wrong, because log base 10 of negative 4, go back to our definition of a logarithm. We cannot take log base b of a negative number. It has to be greater than 0. So right here, we have an issue, and that's why it says non-real answer. And since we get an error, this does not exist. So we have to be aware of why that's happening as we do each of these problems. So there's some calculator things that you can just plug in. But once again, when you press log on your calculator, that's called the common logarithm, and that's base 10. Properties of logarithms, these are derived from the definition. Number one, we're going to talk a little bit about if you have log base a of 1, what would that equal? Well, a raised to what power is going to give you 1? Well, the only way you can get 1 back from any value of a is if it's a to the 0 power. So that's why those two statements are true, is that a to the 0 is 1. Same thing for the second one. If you rewrite, it's a raised to what power is going to give you a back? Well, since the bases are the same, this is a to the first right here, so therefore it must be equal to 1. And so that the first two really just come from the definition of a logarithm and being able to write them exponentially to understand what they equal, and that's true for all values of a. For 3 and 4, it's a little different. 3 is the inverse property. A logarithm and exponential are inverses of each other, so they're able to cancel each other out. And I'm going to talk about this one a little bit more in class in detail as to why this actually works. But log base a of a raised to the x, log base a of a cancels and gives you just x. Same thing on the next one, a raised to log base a of x. These are inverses, they cancel each other out, and you're just left with the x value. Number 4, this is a one-to-one property. This is going to be another important one that we use throughout this chapter. If log base a of x is equal to log base a of y, if the log base a's are the same, and you're using the same base, then it's the one-to-one property to say that x is equivalent to the y value. So once again, we'll talk more about property number 3 in class. We'll be using that one probably the most frequent with the inverse property, so I really want to make sure you understand that. So a couple examples here of using those properties. Solve for x. Log base 3 of x is equal to log base 3 of 8. Well, if we have those logarithms with the same base, then this is the one-to-one property that allows us to say x is equal to 8. On b, log base 7 of 7 is equal to x. Log base 7 of 7, that means that x is equal to 1, and that's because of property number 2. So I'm just going through and explaining which properties we're using on each of these. On example C, log base 5 of 1 is equal to what? X would be equal to 0. You can think about this because 5 raised to the x power is 1. So what does x have to equal? X is 0. This would be, if you're looking at your properties, this would be property number 1 as well. Alright, as we look at example 6 here, log base 2 of 2 raised to the x. So you have a logarithm, and then you have an exponential right here, but the bases are the same. So they cancel each other out, and you're just left with x. This is the inverse property. Same thing with b, 9 raised to log base 9. So you have a base 9 and a base 9, log base 9 as an exponent, so they cancel each other out, and you're just left with 13. Once again, this is the inverse property that is being used. Alright, the last thing that we're going to talk about with logarithms today is their graphs. So go ahead and graph 7a, which is f of x equals 2 of x. This is an exponential function, not a logarithm, but because they're inverses, this is important. So I went back and graphed the exponential function, showed you the t-chart because I wanted you to recognize where those points were. Now, on b, g of x is equal to log base 2 of x. That's the inverse of the exponential 2 raised to the x power. So what should we notice now when we go to do the logarithm? Well, we don't want to plug any value in for x. Not every value works out nicely, kind of like a square root. But here's the thing. If these are inverses of each other, then what is true about the domain and range? They should switch. So instead of being negative 2 1/4, it now becomes 1/4 negative 2. 1/2 negative 1. 1, 0, 2, 1, 4, 2, 8, 3. And so when we go to graph its inverse, what do we get? So there is the inverse of an exponential, log base 2 of x. You can see the shapes are similar, but now this is, once again, instead of having the horizontal asymptote, you have a vertical asymptote. And so that's its inverse. So this is the parent function of log base 2 of x, and those will be the ones that we typically graph. So this is the parent function, so any transformations will be from this graph. Let's talk about a couple of things in terms of the domain and range of each of these. So before, when we did exponential, we said the domain is all real numbers, the range is values greater than 0, horizontal asymptote at y equals 0, and y-intercept at 0, 1. Now go do those same 4 things for its inverse. So go ahead and pause and write those same 4 things down for the inverse of an exponential, which is log base 2 of x. And so now you can see the domain and range switch. Domain is all values greater than 0. Range is all real numbers. Instead of having a horizontal asymptote, we now have a vertical at x equals 0. And instead of having a y-intercept, we have an x-intercept at y, 0. Once again, because those are inverses, you see those switches in terms of those pieces of information as well. What else do we know? Well, remember, we know that these are symmetric across the line y equals x because your x and y values change as well. And so once again, f of x and g of x are symmetric to the line y equals x. F of x has an ordered pair x, y. The inverse of f of x has an ordered pair y, x. And so you don't have to memorize log base 2 of x. If you know your exponential, you know your logarithm by taking the x and the y and just switching them. So let's take a look at a couple examples here graphing logarithms. First, start with your parent function. So if you have to go back and look at that, do so. But also remember, you can just take your exponential function and graph its points the other way. And so that's what I've done right here. Now we want to take these points, and if it's log base 2 of x plus 1 in parentheses, that means it is going to go left 1 unit. So I'm going to take all these points and go left 1 unit. I'm not going to try to plug numbers in, because if I do that, I can guarantee you're going to struggle because logarithms are so new. You don't have that relationship that you do with other functions that you're very familiar with. So there's log base 2 of x plus 1. The graph is shifted to the left 1 unit. You can see how the vertical asymptote is also shifted 1 unit to the left. So I don't want to see that line go over that vertical asymptote. Go ahead and try 8b on your own. And so once again, you can see my parent function in red. It's going to get shifted up 2 units. So I took all those points, moved them up 2 units, regraphed it. Vertical asymptote stays the same because you're not moving it left or right. Obviously, some of the other things change in terms of your x-intercept. But there's your log base 2 of x plus 2. Realize that is not in parentheses. So this happens first, then you add the 2. That's why it's a shift up 2 and not a shift left 2. Look at the difference between 8a and 8b. So that is it in terms of notes for our section 3.2 logarithmic functions and their graphs. Once again, I want you to write down kind of what your conclusion is to this unit. What are those important things? And then we'll discuss that in class as well as to what you wrote down and what things you feel are important that you needed to pull from that unit or that section.